Hey folks, I've got a new idea for a little project I want to make here. Designing a little switching power regulator, and I thought it'd make a good opportunity to make a little series of videos to show what I go through when I'm you know going through the process from first conceiving an idea of a project I want to build to component selection to making the layouts for those components on the boards, the footprints. Um, After that, putting together the circuit for what I want to do, laying out the boards, and then finally how those boards end up getting assembled after they get ordered. So I thought I'd start the video here. We'll do this first video as a kind of an introduction and talk about the project and what I want to do with it, and then start on a little bit of component selection. We're not really going to cover on all of the components, but we'll get the general idea, and we'll talk about what I'm thinking about when I'm selecting these first kind of major components here. So we've got our text document here, and so like I said, I want to make a little switching regulator. Specifically, I want to make this for a Raspberry Pi. Uh, and So these things aren't terribly power hungry. We don't need many amps, but they can take a fair bit. So I'd say at a minimum I want my design to be able to handle say 1.5 amps at 5 volts, and I have a 12 volt power rail, and it's not specifically 12 volts. It's really 13.8 volts is my fully charged lead acid battery bank, and it powers a number of things around my office and the shop here. But so that's going to be my main source for running these. So I'm going to say a 12 volt supply voltage, and the other part of this is that this is in theory battery powered, and the Raspberry Pi itself is going to take a not insignificant amount of power. So I'd like the regulator itself to be relatively power efficient. Uh, Switching power supplies are good for this. You can do linear regulators, but the problem with linear regulators is obviously that when you drop from 12 volts to 5 volts, you have to drop all that in heat, so they can get pretty hot, and they're not very efficient. They're going to be Their efficiency is directly proportional to how much you're dropping in voltage. So especially when you get higher differences between 12 volts and 5 volts, they can be pretty inefficient. Whereas a switching power supply could be 90+% efficient. So those are kind of my main thoughts. Um, there's going to be kind of a few major components to this. Is there's going to be a switching regulator. Uh, this is going to be handling the frequency and turning a MOSFET on and on. Often these have the MOSFETs built into them, and so that'll kind of be the core of the functionality. There's going to be the main inductor that's actually going to be the kind of the charge storage for the switching regulator, and so that's going to be an important component here. Um, Switching regulators also, as they are by the name switching, they switch power on and off to generate the output voltage, and so by doing that, their output voltage gets to be a little wavy. Ideally, powering a DC device, you want to power it with as smooth of a DC level as possible, so our output capacitors. And then, it's also a good thing to do input capacitors, just to make sure that your inputs, especially in switching regulators where the sudden inrush of current and outrush of current, because you're switching these connections on and off, making sure that you have a low impedance path from your input voltage, your input current source, to your switching regulator and your inductor is an important factor. So when we're looking at that, we're going to want to make sure that we have capacitors here with pretty low ESR values, larger traces, and then keeping those traces short between the switching regulator, the inductor, and the capacitors, and then adding all those three together. Make sure that we get the best current path possible. And then you're going to have your input and output connections. I'm probably going to end up using a footprint that'll be just some holes on the board with soldering points, like you'd have any pin through hole. They'll be rather large holes, and I'll probably make the holes spaced so that I can use Anderson power pole connectors. I'm rather fond of them. They're a wonderful little genderless connector if used properly and can handle high current. So that's kind of the idea of what I want to do with this. I'd like to make it as inexpensive as possible, as with all things in life, but I want to make it of decent quality as well. So that's the trade-off, and figuring out what good components we can use that will meet all these requirements and get what we want done for the least amount of total cost. So what we'll do is we'll take a look at sourcing some components, figuring out what exactly we want to use, and then after that's completed, then we'll start looking at laying out the schematic here in Eagle. Once the schematic is finished out, we'll move on to laying out our board, and then once that board is finished, we'll work on exporting our Gerbers, setting off to a fab house, and then once we get the boards back, all the parts in, then we'll actually take a look at assembling. And so all those will be different videos here in the series. But first off, we're going to look at our part supplier here, and I like to use DigiKey. There are a number of different options. DigiKey is one of many various suppliers. I find that they tend to have good prices and good availability, and to my neck of the woods, they ship very quickly. So I can use the cheapest USPS shipping, and they get it to me within 2 days. So it's really nice for me, and they've got a big selection, so it works out well. So, like I said, when we start looking at the list of requirements here and what's kind of the major components here, really what we run into here is that the switching regulator, that IC, that chip, is the heart, the core of everything else that happens on this device. That's really what we're building here, is a switching power supply. The inductor, the output capacitors, and the input and output connectors are really just, tacked on to our switching regulator. And so we need to find this part and make sure it meets our output requirements, our input requirements, and our efficiency goals. So really what we look at here is when I go to DigiKey, we go to our products section here, load it up, and I'm going to do a search here, and I'm going to do search for a regulator. So they've got a whole pile of different options here. So I'm going to go to these voltage regulators, DC-DC switching regulators. Now, this is a big category. We've got, at this point, 22,000 different parts that do various different things and may or may not actually fit our needs. And so that's where our parametric search functions here come in, and you can see there's a lot more that don't fit on my screen. So we're going to go and try to narrow this field down so we can find some options we want. So unfortunately, this can be kind of a long period of time is on some of these parts where there's a lot of different options, is narrowing down what it is that exactly you want. But if you take the time, then hopefully it'll end up working out in your favor. So I'm going to start by narrowing the field by our current output. Like I said over here, I want at least about 1.5 amps out, but more would work fine too. So I'm going to scroll down here, find my 1.5 amps, and keep scrolling, hold down my shift key, and just select everything between 1.5 and the maximum. And I'll apply those filters. And while I'm at it, I'm going to apply filters based on in stock, because there's no use in having DigiKey show me parts that I can't buy. Now, the question comes down to is our voltages. Um, since we've selected our current output, really we want a 5-volt output. But most of these regulators are going to be adjustable in that there's going to be a resistor network outside of the device that allows you to set what voltage you want to come out of it. And so while we can ask for adjustable, we can also just put in fixed here as well just to see what they show us. We only need one output, so I'm going to select one. We'll throw 1 or 2 in there if they show me something fancy. And so we'll narrow the field down a little bit more. And you'll see that as I'm narrowing this field, I'm narrowing the field each step by 1 or 2 different categories. If you start adding lots of categories together, you can actually end up in situations where you select categories that don't exist. So as you narrow the fields, as you narrow your categories, other categories will have fewer options because as you choose, say, there were only 5 fixed components, and that's a vast understatement. But say there were only 5, and you had asked for, one that was a, synchronous and unsynchronous rectifier. You had selected both. Well, maybe that didn't exist. They both individual options existed in the overall field, but now that you've selected that you want a fixed regulator, none of those options might have that. And so I go down and I select 1 or 2 fields at a time and keep applying those filters and narrowing those down so that these large fields that have a million options, they get smaller, so it's easier for me to find. And 2, I start to see where the limitations are. So you'll see, we've already, just on those couple first selections, narrowed the field from 22,000 to 4,000. Now, 4,000 is still a very large value. So we're going to next look at the type here. So specifically, we were talking about coming down from a 12-volt supply to a 5-volt supply. So we're going to want a step-down converter. These are, commonly referred to as a buck converter. So there are a lot of different buck options here, so I'll just select all of those. Some of them also include step-up converters, and that's okay, but really what we're after here is the buck options. So I've selected those. We'll apply those filters as well. So dropped another 300 or so off of that. So now we get into these fields here, which are kind of specific because none of these other options are terribly important to me. We'll make a footprint for whatever we find, so I don't care what package we're using. Operating temperatures, these are going to be in my house. We're not going to extremes of minus 55°C, so I'm not terribly concerned about that. It doesn't really matter to me whether these are synchronous or not. And we've already selected our current output being 1.5 amps or greater. Switching frequency doesn't terribly matter to me, and so really it comes down to what are our voltage input ranges and what are our voltage output ranges. And so we start going down here and say, 0 to 14.5 volts. Okay, that's going to be an option for us. These ones don't look like they go high enough, adjustable to these values. And so we're going to scroll down here. Adjustable doesn't say specifically, but that could work. So we're going to start selecting all of these options here that actually fit the range of including a 5-volt output. And like I said, this can be something of a long and tedious process because lots of times these fields can have just enormous amounts of different selection options. That's both the benefit and the curse of these wonderful sites and providers like DigiKeys, that they have millions of options, and you're stuck having to actually choose between those options. So hopefully here it won't take me too long, and we'll filter this down a little bit. If I decide it ends up taking a little bit too long to sort through this, then I've already selected this part, and so we can skip ahead to that. So as you see, and each field has a, kind of different method on which they usually sort these things. In the case of, adjustable voltages, most often you'll see that, it's going to be sorted by number in the ladder field, and then, the same will apply to the first field. So, but you'll see that your minimum voltage will start creeping up, and then your output voltage, your maximum voltage, I should say, will go cyclically. So, we were at 39, and now we're back at 4.4, and it'll creep back up towards the 40s. And so, as we go through that, we just have to make sure that we're watching it carefully, and we only select the parts that are good for us. The other thing you'll note is that I'm avoiding values like exactly 5, just because, often when you have regulators like that, they're not going to be as efficient or do as good of a job, or have a harder time running at the edge of their working range. And so I'm trying to avoid having to deal with pushing that, and so I'm giving myself some headroom and not choosing the regulators that are limited to exactly 5. So as you see, we were at 0.8 a minute ago, 0.97, 1 volt as our minimum voltages. So that's just fine. As we're creeping up, pretty soon here we're actually probably going to hit minimum voltages that go actually above our 5 volt value, and so those will no longer apply to us. So looks like we're getting pretty close here, so I'll finish out this list. But as you can see, if you're looking at parts that have more options or different options, or more in a given option, you can see that these values can take a while. Or if you don't have very specific requirements, you don't know what you want yet, that can also take a while, just because if you leave your requirements as vague, then it's hard to narrow them down. So that's kind of the trade-offs here when we're selecting parts and trying to narrow the field and find what we want. So yeah, we're creeping up here to 2.5 volts. I expect here pretty shortly we're going to hit higher voltages. So yeah, 3 volts. That could work. That could work. Oh, so now we're at our 5 volt minimums. I'll include these ones that specifically list 5 volts, or 5 comma whatever. But otherwise we're above our useful range, and so I did not mean to do that. So we will scroll back over, apply our filters, and come up with what we got. So now we've got 2,500 components. A lot of them are going to be various things. You'll note that some of these things say like a minimum of quantity of 300, or 3,000. Obviously I don't want to buy 3,000 of these. While at 3,000 they'll give me a good price, it's still a whole pile of money. So what I'm going to do is I'm going to tell DigiKey that I want 1, and I'll submit this, and then so it'll only show me options in quantity of 1. And then the other part of this is that they have different ways that it comes. So let's scroll over here. Yeah, so they say, this is the packaging field. So this is the cut tape option, and this is the DigiReel option. Basically, most of these components come from the manufacturer in paper or plastic tapes that you peel a protective covering off of. And so what they'll do is that, these tapes come on a reel from the manufacturer, and so DigiKey will cut your part you just cut the tape and send you the number you wanted. A digi-reel is where they'll do the same thing, but they'll put that tape onto a reel if you were doing, uh, you know, machine manufacturing. You're putting these into a pick-and-place machine. Those machines need your parts to be on a reel to work properly. So we're not doing that. We're assembling it by hand, and they charge a surcharge to put them on a digi-reel. So I'm going to go to the packaging field here as well and say I'll accept bulk, I'll accept cut tape, I'll accept trays or tubes, and cut out these digi-reel options. So we'll apply those filters as well. So we've still got our quantity of 1. We've removed our other options for packaging that don't really apply to us, and so now we can also sort by price. Excuse me there. So now we have them showing us parts in the quantities we want, in the packages we want, sorted by least price. And so then we start looking at what are our options here, how do they compare to each other, and start looking at data sheets. In this case, I do most of my work as surface mount stuff, so I'm actually probably going to take these pin through hole parts out because they don't really apply to me either. So I'm going to do surface mount on the mounting type. And apply our filters again. And then for some reason DigiKey likes to make you redo the sorting here on a unit price. So you got a whole pile of options here. You can see one of these I've already looked at. But basically it's going to be up to you in your specific thing. You're going to probably have to look at a few. I've got a few different ones here. That's actually a different thing. So I've got one here, different packages, different things. These two happen to be from the same manufacturer, Diodes Incorporated, but they're from different lines. These are AP3211s, and these are AP3503s. So they're going to have different characteristics, and so you're going to have to look at the data sheets and see what characteristics you like. In this case, I have the data sheets up, and so most data sheets are going to start with a general description here of what they do. This one over here, high efficiency up to 92%, output current up to 1.5 amps, and kind of give you a basic overview. And then they also give you a general idea of what applications that they think this part is a good fit for. So the same thing applies to both of these. You'll see that this one has a lower switching frequency than this one. For my cases, it doesn't really matter too much, but it might matter to you. This part over here does have a higher output current capability, and it has a higher potential efficiency. So they also quote it as a high efficiency at a light load, because I don't really expect to be running these things anywhere near 3 amps. I'll probably be running them at 300 milliamps. I'm hoping that that this part might give me better efficiency because I'm not running it very hard. Our input voltage range is 4.5 to 18 volts, which easily meets our 12 volt supply. So, when we're talking about a lead acid battery as a supply there, we're really talking about, it being fully discharged on a lead acid battery at 10.6 or 7 volts. And then, during charging, you can see voltages as high as maybe 14.5 volts. And so really giving us some headroom on either side, just makes it a bit easier so that we don't have to worry about what we're plugging it into. So also allowing us lower input voltages here gives us the option of, maybe I don't want to use a lead acid, I want to use a pair of lithium polymer batteries that, together are going to be at 8.4 volts fully charged. And so as those drain, you'll still be within your input voltage range for this sort of a regulator. So then we start looking at, the pins on there, what their functions are. It's going to go through and say what each of the, in this case, 8 pins do, and kind of a general overview of how they should be connected together. We've got different functions. And then in this particular case, because this is a regulator, they're generally probably going to have to dissipate a fair bit of power in there. That's where your 95% efficiency comes in. That other 5% is going to be dissipated as heat. And so they have an exposed metal pad on the bottom of the package. And so when we're designing our footprint in Eagle, we're going to have to make sure that we leave some copper available on the bottom that we can solder this to. So they're going to give us generally a functional block diagram, like they say here. Ooh, there's basically a high-level view of the insides of the parts. What are the general components, the functional blocks of how this part is going to work. They'll give us some information about their numbering scheme. So this is our part family number, and then they'll say have an option a field there for what package it is, what packaging it comes in, and then perhaps any ROHS or other specialized things. Often they'll have a normal temperature range and like an industrial temperature range, which will also be another option that they'll tack onto the part number. So as you see here, our AP3503E corresponds to the part number DigiKey has, this AP3503E, and we see MPTR. So the MP is our PSOP 8 package, and our TR is our tape and reel packaging. If we didn't have the TR, then it would come in a tube. So I don't have the G1 at the end. Actually, it looks like I do. So the G1 is just means it's green, whatever Diodes Incorporated defines green as. We'll have our electrical characteristics. In this case, our absolute maximum ratings. These are what they rate the part to without destroying it. If you exceed these, you'll destroy it. Most likely. So generally, these are good things to be aware of, but you want to be designing your circuit to make use of your standard electrical characteristics here. So in this case, they specify our input voltage here. We'll use our input voltage as an example, but they're specifying a minimum of 4.5 volts and a maximum of 18 volts. Whereas if you look at our absolute maximum ratings, they can say up to 20 or minus 0.3 volts below the ground rail. You exceed either of those, then it's going to most likely cause problems for the device. And then they start talking about functional characteristics, as well as what each of the pins, if they have different functions, might exhibit. So like the enable pin, they'll say what voltage switches between enable and disable. So they'll say that below 1.5 volts it'll be disabled, or above 1.5 volts it'll be enabled. They'll also, in this case, they're also listing a hysteresis voltage, which means that 350 millivolts above or below that, is going to be a difference between when it turns off and when it turns on again. So these are, it's going to tell you about all the different functions of the chip. And, in this case, what we're looking for is making sure that our input voltage is good, meets our range, and then checking that our current output meets our needs. The maximum high side current limit is they're listing it as 5.6 amps. That's good. They rated it at 3 amps is what the rated current is, and so that's going to meet our needs. But this is what the most we could expect to see out of it for short periods of time. And then in this case, because this is an adjustable regulator, we have to feed it a reference so we can set the voltage. And so that's where this feedback voltage comes in. So what they're going to do is they're going to look at what voltage you feed into it and compare it to this 0.925 volts value. If the voltage you feed into it is lower than this, it's going to try to crank the voltage up. And if it's higher than this, it's going to try to crank the voltage down. So we will need to set a resistor divider connected to the output of the device to make sure that when we hit 5 volts on the output, we're getting 0.925 here into the feedback pin. And so that's part of the design we'll cover later. Often they'll give us nice little graphs here that show us what kind of performance that they've tested it at. In this case, so we're doing a voltage output of 3.3 volts. They're using a 10 microhenry inductor at room temperature. Then they give us 2 lines here, one with the input voltage of 5 volts, that's this solid line, and then one with an input voltage of 12 volts, that's this dashed line. And so then they're saying, okay, our x-axis here is our load current. This is a logarithmic load current graph. And then our efficiency value in percent. So in our case, if we're looking at, that's 100 milliamps, 200 milliamps, 300 milliamps. If we're looking at this, we're looking at 90%, 95%, between these two values. So as I bring the voltage output up, and I'm still going to be feeding it with V in as about 12 volts, because they're closer, I'm probably going to expect it's going to be better than the 90% efficiency that this is showing here. I'm not sure I'll see the 95% efficiency that we get here, but I might expect to see somewhere in the middle. So that's a good value for me. I'm for a switching regulator, I'm pretty happy with 90% efficient plus. Then they're going to start rating various other functions that may not necessarily apply as closely to us. This is our quiescent current versus temperature. If the device isn't necessarily doing anything, it's not regulating, how much power is it drawing versus the temperature that it's running at. That's not terribly important to me. It's pretty much going to be on all the time. Feedback voltage versus temperature. They're saying that the feedback voltage, that 0.925 volts value that we saw earlier in the data sheet, that will actually change slightly based on the temperature of the device. So they're going to rate, we're going to rate that based on, temperatures we can expect. 25 volt, 25 C, about room temperature, 50 C if the device is running warm while it's regulating. It's going to be pretty close to the rated value that they're specifying. And then they're saying what sort of output voltage, if we've got a set voltage, say at 3.3 volts. In this case, it looks like they're set at about 3.35. And what's that voltage going to look like as you crank the current up? So there's a pile of graphs. Sometimes they'll even be nice and give you oscilloscope traces of how they're doing things and while they're testing things. So you can see how the device might perform. And then what's really nice is some of these providers, actually, excuse me for a second here. Thank you. Some of these manufacturers will provide typical application circuits, which is basically a example schematic of how they've set these things up and how they think is a good way to set these up to work well. So this is actually going to be very close to what we end up setting up when we move to create our schematic using this part. So as they show here, we've got our input capacitance that we talked about before. We've got our output capacitance that we talked about before. Critically, the output inductor that we talked about, and then they have a few other parts. So these two resistors here form our feedback network. See how we've got it connected to the output, feeds into the feedback pin, and then connects to ground. So this is our feedback to set our voltages. And then we have different pins on the device that help it function better. Bootstrapping and compensation pins that they will ask us to connect capacitors or resistors to help the device run better. And often that's just because they, we could have different requirements than their design might say, and so we could change those, or it's expensive to put those on the die or hard to put those on the die in the chip itself, and so they'll just say we'll connect this to a pin. You have to provide this externally, and that's how it goes. And then lastly, kind of the important thing here is that they give us a drawing, mechanical drawing, of how these things are physically. How if we look at edge of pin to edge of pin, how wide is this? How wide is the package itself? How wide are the pins? What's the spacing between the pins? In our case, it won't matter so much for the thickness of the device, but that can matter for some applications. And then they don't provide one, but sometimes they'll provide a separate mechanical drawing for just what they recommend the footprint on the board should look like. And so that's kind of the walkthrough of what the data sheet on one of these devices is going to look like. So with that said, I think this part will make a good option for me. So I'm going to move forward with trying to use this. So I don't need these extra parts here that I don't care about as much anymore open. So I'll close those out. And then we'll start looking at inductors. So we're going to run through the same thing. We'll go to the products here. And I'll do a inductor. And I'll do a fixed inductor, which means I'm just asking for an inductor that has one value. Their data sheet here suggested a 10 microhenry inductor, and so that's what I'm going to ask for here in our inductance field. We'll apply that filter. And the other important thing here is that the inductor here needs to be able to handle a fair bit of current, both in its rating and its current saturation. If the inductor gets saturated with current, then your efficiency is going to drop off. So we need to make sure that our current saturation value is more, by a fair margin, than what we're going to expect to need. And so I'm going to go here, since our regulator's 3 amps plus, I'm going to give myself some margin. I'm going to ask for 5 amps plus on our saturation value. And I'm going to do the same here on the current rating. So I want the inductor to be able to handle that sort of current continuously. So I've got those selected, and we'll apply those filters. So it's going to come back to me with a bunch of parts now. Again, I'm going to go in stock. I'll do the same deal here, is that we'll take out the real options. And I'll select a quantity of 1. And then I'll sort by price. And so here we are again. We've got a narrowed down list. In this case, our tolerance doesn't matter too much. We're not doing any filtering with an inductor. Filtering with an inductor can be more specific on tolerance or Q ratings, quality ratings. In this case, we just need it to be an inductor of about this size. In this case, we're talking about fairly big inductors that can handle a fair bit of current. So most of the time you're going to see these with a ferrite core. Different inductors may have different core material. You may see them with different types. These are all going to be wire wound because they're handling quite a bit of current. You may see them as little chip inductors, which can work fine. They just have different purposes. Now, in my case, I also do a lot of radio work, so I like to keep the radio spectrum as clean as I can, so I'm probably going to go for a shielded inductor rather than an unshielded inductor. So I'm actually going to go up here and ask for shielded. So now it's got shielded inductors that meet these needs, that handle the current, and are sorted by price. So in this case, this one here would handle all the current we need. It's shielded, and it's the cheapest one we've got. So I think we'll look at that. I've actually already got it pulled up right here. So sometimes DigiKey's nice enough to give us a little picture of what it looks like. Sometimes they don't have a picture, and that's okay. So we'll look at their data sheet again. Lots of times on passive parts like inductors or capacitors or resistors, they come in families, and so the data sheet is going to cover the family, and so you'll see that they cover a whole different range of values and tolerances in this family, and so they're specifying the data sheet to cover all of these. In this case, they're also giving us product dimensions. They're saying it's 1/2 inch square, 1/2 inch this direction and 1/2 inch in this direction, you can see here. They're saying it's 0.335 inches thick, which doesn't matter too much to me. And also, like I was saying earlier, sometimes they give a recommended layout, which is, you know, how you should create the pads on the board. So in this case, they give us mechanical dimensions for how to generate the copper pads that this thing will solder to. And then, you know, on these things, like I was talking about, you'll have your reel with the tape in it with the cover, and so often they'll give dimensions on the specifications, if I could speak, on how these parts will come in the reel, so that when you put the reels in your machine, you can tell it how far apart the parts are in the tape and where the holes are in the tape, and etc. We don't really care about that, so all we really care about is our recommended layouts, our product dimensions, and making sure that they fit our requirements. And so with that, we've kind of selected our two major components here: our switching regulator, our inductor, and our output capacitors and input capacitors. We're pretty much going to follow the same goals. Is we're going to start looking at our values, narrow them down, and select what works well for us. In this case, you know, points that we're going to be looking at carefully are related to the voltages that these things can carry, as well as their ESR, the equivalent series resistance of these devices. Because we're dealing with higher currents, we want to make sure that these things can supply these currents very easily and quickly. And so making sure they have low ESRs and good characteristics is going to be important there. So that's really going to be our selection. And then usually, you know, with capacitors, you like to overrate them on voltage. If you only expect to see 5 volts on the output, you know, buy a capacitor that's rated for 7 volts or more, you know, 25% or so. If you want to give yourself some extra headroom, call it 50% or even 100%, double it. You know, our input capacitors, I'd probably rate those, you know, we're going to see, you know, 12 to maybe 15 volts at the max in. You know, I'd rate those as 25 volts to 50 volts. Higher doesn't hurt, but that's where I would put them. And then the input-output connectors, that's really anything you want. I just happen to like the Anderson power poles, so I'm probably going to make my connectors, you know, on the board compatible with these, so I can keep using them. And that's really the initial design, you know, design selection steps here on when we're talking about making a regulator. I'll go through in the next video of, after I've selected all the rest of the components, the capacitors, resistors like we see here in various locations on the schematic. And then we'll talk about how we translate this schematic over to our schematic editor here in Eagle. And then we will work on setting up that schematic. And after that, the next video will be setting up the board. So we'll see you next time for setting up the schematic and creating the part footprints. So thanks for watching, and I'll see you soon.